Thank you very much, Antonio. I'm Will Hornby, as Antonio said, a subject advisor and the subject development lead for mathematics and further mathematics at OCR. So I'd like to welcome Keith, who is a colleague from MEI, who's done a lot of work on the maths and further mathematics qualifications for MEI, and I'm sure his presentation is going to be very interesting on MEI's further maths. So without further ado, I don't want to take up too much time. I'll pass across to Keith.
Thanks, Will, and thanks, Antonio, and thank you to everyone who's come along to this webinar this afternoon. Thank you for giving up your time. I do hope it's helpful and useful. So here is our title. And I'm going to do a very small amount about the further maths spec in general, but most of my session will be about a particular topic, just one or two little observations about complex numbers, which may be of interest or of help to you in your teaching and planning. I'm very happy to take questions, and I really would encourage you to fill in the chat box with your questions, and I might answer them as I go along, or I might answer them at the end, depends how they seem to fit in. Sometimes, of course, in sessions like this, people ask questions, and I'm going to answer them in 5 minutes' time, and I hope you don't mind if I leave the question for a little bit. As Will says, I work for MEI, a wonderful job. There's my email address. MEI is a maths education charity, and we're not an exam board. That's really important to say. OCR is the exam board, and we've spent the last 2 or 3 years developing the specifications that have now become OCR Maths B, MEI, but now we hand it over to OCR. They are the exam board. They run the live exams, and we, of course, at MEI continue to support and offer resources and give all the help we can with teaching and learning of the qualification. I'd be quite interested in knowing, it would be helpful to me now and later, how much experience you may already have with the MEI spec. I'm sure some of you teach the current MEI spec, and some of you may not. So you should see a poll in front of you, and it would be very helpful. I can see some people filling it in, which is great. Thank you very much indeed. That's very helpful. As I say, please do ask questions if you want to as we go along. So I'm going to show you now, that's what the spec looks like. I'm going to show you that web page. In case you haven't seen it, there's a couple of pages on the MEI website, one about maths and one about further maths. And just to show you for 5 minutes some of the range of support that we offer people who are teaching the MEI spec. So you should now, or very soon, see a page from the MEI website. And this is the further maths page, and there's a quick link at the top there to maths, in case that was the page you meant to go to. A link here to the specification, that's on the OCR website. And on the OCR website, if you go to the page that is linked to there, you'll find the specification and sample materials as well. One of the advantages, I think, of the further maths, of the MEI further maths spec is the range of options you have. Everybody has to include at least 50% pure maths. There's a 50% sort of common core of pure maths in all of the further maths A levels, and then there's up to 50% for options. And I think we have a wide range of options and lots of flexibility in how you use them. That makes it complicated, but it's only complicated because when we asked teachers what they wanted, they all gave us different answers. So we've tried to give different possibilities for you to choose from. It's not complicated once you've decided what you want to do. you just decide and get on with it. And one of the small advantage we have is that you can choose 2 options or 3 options to go with the common pure topics. Moving down a little bit, these links here under the specification and exams section, those are links to half a dozen presentations, 15-20 minutes long. The first one is an overview of the further maths spec, and it explains the choices you have and gives reasons for some of the decisions we made. And then there's a presentation on each of the strands. So you could look at the statistics strand presentation and get a sense of the content that's there, the reasons we have for putting it there, sort of design decisions, if you like, and some of the things that might be helpful to know if you were thinking that statistics is one of the options you might like to choose. The sample exam papers, I think I said this before, are all on the OCR website, of course. And then we get down to support. I'm going to say more about this, in fact, in the next webinar, so perhaps I won't say much about this now, other than to say that here you can register for what we're calling the MEI staff room, which means that you intend to teach the MEI spec, and you sign up for the MEI staff room, and that gets you access to some extra free resources for the MEI spec and support from MEI, and as well perhaps support from teachers local to you who are teaching the spec as well. So I do hope that you'll register for the MEI staff room. I'm now going to go back to the presentation, which I hope will be a smooth process. And here we go. So now to the main part of what I want to present today. And this is a little strange doing this online because we're going to be discussing maths and how you might teach it. And it would be nice to be interactive, and that's going to be quite difficult. You might like to have a pencil and paper ready because I might invite you to try some maths, or you might want to jot some things down as you go along. Here are my 4 headings, something to think about. So a bit of maths that I found that intrigued me when I found it, and it would be, I'd invite you to have a go at this as well. So here we go, something to think about. And I'm now going to share with you a GeoGebra file, which some of you, I'm sure many of you will know about GeoGebra. It's a very powerful piece of software. It's absolutely free. And one of the things it does is draw graphs, as I have here. I've defined a polynomial function, a quadratic polynomial function, ax squared plus bx plus c. And my 3 sliders allow me to change the coefficients, and the quadratic should move. Sharing this across the internet has its risks, but I hope that you can see that as I'm changing b, the coefficient of x, the quadratic is moving. Interesting to ask what the locus of the vertex is of this quadratic, but that's actually not what I want to do. Mustn't get carried away. So I'm going to ask GeoGebra to plot the roots of this quadratic, and you should see it's plotted A and B there, no surprises. And as I change the coefficients, of course, the roots of the quadratic show up clearly enough there. No surprises there. But there's something else that GeoGebra can do is that it can plot complex roots. If you want to do this, by the way, you must, when you first enter the polynomial, enter it as f of x equals, so that your polynomial has a root, has a name. You can see me typing complex root f here. And now you can see Z1 and Z2 plotted here. And what you've got to imagine is that we have an Argand diagram superimposed on the coordinate plane. So that the two roots, there they are written on the left-hand side, one of them is 3.07 plus 0i, and the other one is negative 0.52 plus 0i. And there's no surprises there, really, I think. So let's now have a go at this. I'm moving C and B around, and as the points get closer and closer, this happens, and that's all fine. And look at this. So I've now got I don't have any real roots, but I'm now seeing the complex roots appearing on the sort of superimposed Argand diagram. And you'll understand why there's a bit of symmetry going on there, because we've got complex conjugates of each other as the two roots. I wonder what's going on here. I think this is amazing, or at least puzzling, or at least worth asking a question about. What's the locus of the roots there as I change B, I wonder. Anyway, that's got me thinking, and it just struck me as a little bit interesting. I'm going to just choose a particular value, -3 here, and I'll change C, and I'll notice that when I get there, is it about there, that at the value 1, the vertex of the quadratic sort of coincides with one of the complex roots. And I'll come back to that in a moment. So there's a little diagram to think about, and here is a couple of questions to think about based on that. What's going on there? Well, the first thing you'd notice is that when we have a polynomial, a quadratic with a plus c there, and we try to find its zeros, then you do get this symmetric situation, don't you? The two roots are going to be symmetric about the point 3/2, or about the value 3/2, because of the plus and minus. And that symmetry is going to be there whether the bit on the right is real or complex. I think that's the point I want to make. We've got symmetry about 3/2, whether the plus or minus bit, the bit you add or subtract, whether that's real or complex, you've got that kind of symmetry. And that's true in the general case. You get symmetry about -b/2a, whether or not what's over here is real or complex. Just have a think about that then. Here's the last, more or less the last picture you saw in GeoGebra. And I've got 2 or 3 questions for you. I haven't asked a question about the locus, because I only just found that out about 10 minutes before the presentation started, when I was just testing I could do this. But so for what polynomials, I mean for what quadratics actually, I mean quadratics in both of these questions in the yellow box. What quadratics does the vertex at y equals 1 coincide with a root with imaginary part 1? And I'm just interested to see whether you might be able to have a play and think about that. And then a different challenge. So I've got my symmetry about 3/2. And if you look at my blue points A and B, I wonder if it's possible to have a quadratic with those as the roots. And what might that quadratic be? Those 2 points are symmetric in some sense about 3/2. I wonder if there's a quadratic which has those roots. I'll give you just 3 minutes to play around with that a little bit. See if anything strikes you as interesting. Of course, we don't have facilities really for having a proper discussion, but 2 minutes of playing around might be of interest and help the problem intrigue you. I have a question here which I'll answer. Thank you for offering this question. And it says, it's only been written to me privately actually, but that's fine. May a school register for the MEI staff room if only offering the further maths spec? Yes, you probably know that maths and further maths are completely different specifications now, and you can do maths with one exam board or one specification and further maths with a different specification. And yes, I don't see why not. Why can't you sign up for the MEI staff room if you're doing the further maths, only doing further maths with MEI? I'm sure that's fine. I'll move on now. I don't suppose it's very easy to share any of your suggestions with that bit of maths, because I do wonder if you're thinking what I'm thinking, and what I'm thinking is what happens with a cubic with my diagram. So I'll try sharing GeoGebra again, and I'll show you how I got this. So I'll type in a cubic. It asks me whether I want sliders, and I do. I'll move it all across a bit, move this across a bit. And the command you put in here, if I can remember right, is complex root. There it appears, complex root of a polynomial. The polynomial is called f. So there are my 3 complex roots. And you might think to yourself, what's going to happen? What will these roots look like as I slide around and only end up with 1 real root or 2 real roots? So let's have a try. I could do it like this. So there's 2 real roots. And I've still got the conjugate pair. And you're kind of wondering, is that conjugate pair lined up with that minimum point or not? I don't think it is. Because of course, you don't always have a minimum point. And you get something different going on if you do it like this. So I wonder what properties that triangle has. It's clearly isosceles. wonder if there's anything else I could say about it. Anyway, I mustn't get carried away. I just think there's something interesting going on there to explore with complex numbers. Whether you would do any of that in the classroom, I don't know. You've got to be really clear about what's an Argand diagram and what's a coordinate plane, so you've got to be a little bit careful. But nevertheless, I thought I'd start with a bit of maths that had interested me. And now we'll get back to some pedagogy and thinking about how you might introduce complex numbers. And this thinking came out, Will be interested to hear, this thinking came out of something that Ofqual made us think about when we were trying to get our specifications accredited. And I'll say what it is in a while without giving any secrets away. When you introduce complex numbers, I'm sure that many of you will have thought of the idea that during the kind of the history of mathematics, people have invented different numbers. Our students often find the idea of complex numbers strange. And so you might point out that in previous generations, fractions were thought quite strange, and so were negative numbers. So that top equation, x plus 2 equals 8, there's no problem with that. We can think of an answer. If all we know are the counting numbers, then it's absolutely fine. I know what x stands for in that equation. And I even do in this one. It's a little bit harder, but after a while I can think of a whole number. I can think of a counting number so that when you multiply it by 3 and add 2, then you get the answer 8. But as soon as I get to this one, I have to declare that there isn't an answer. Or I invent rational numbers, and there is an answer. But rational numbers are very strange, aren't they, really? The idea that a half and 3/6 are the same number seems very odd at first, if you can imagine the first few generations trying to cope with rational numbers. And then by the time we get to x plus 2 equals 0, we've had to invent a whole load of other numbers, negative numbers. 0 comes in there, of course, somewhere. And then at some stage, we'll have to invent irrational numbers. And of course, there's a whole interesting history about irrational numbers. And you may be aware that in A-level maths now, some work is expected on proving that root 2 is an irrational number. And so there's this kind of history of inventing numbers to solve equations. At least that's one way of thinking about it. And eventually we get to this equation at the bottom, and here's another equation that we can't solve. And so let's invent a number to solve that equation, and we'll call it I. Incidentally, some of you who use the current MEI spec now will be used to using J for I, if you see what I mean. And we've decided, momentous decision, to go to using I for one of the square roots of -1. Have I skipped ahead? No, I haven't. And it turns out, and this is an important thing to say, that in some senses, this journey is now complete. In some senses, there are no more equations to write down, or rather no more numbers to invent. In some senses, we've finished the journey. So that polynomial equation at the top of the screen, that 5th degree equation, it has complex number coefficients, and yet it has 5 solutions which are complex numbers. I have no idea what they are, and there's an approximate method that would get close to them, but I know for sure that I don't have to invent new numbers to solve that quintic equation. Nor do I need any new numbers to solve cos x equals 2. But the answers to that, the solutions to that equation are complex numbers. E to the x equals -5 as well. And perhaps it's important, that certainly at the end of your A-level further maths course, to come back to those last two. Here we are, solving cos x equals 2. So don't lose that awe and wonder moment of showing how astonishing complex numbers are, the depth of the things that they can do, and this sense in which the journey is complete. The beginning of solving cos x equals 2. Now, I'm going to suggest how a little approach to introducing complex numbers has some advantages. It doesn't mean you have to do it like this. I'm sure there are plenty of ways of doing it, but I just want to point out a couple of different things for you to think about. So if I'm solving x squared equals -1 and I decide to call the answer I, then the second line here, x squared plus 1 equals 0, of course that's the same equation. So I had better be one of the answers. But if I try to solve it using the formula, I get two solutions, plus or minus I. So it had better be the case that not only is I squared equal to -1, but negative I squared is -1. And then if I try to solve the third quadratic equation, and I use the formula in the normal way, I've carefully chosen it, in fact, so it has a discriminant of -1. And so I'm going to get the two answers that I've written out there. And actually, I seem to have introduced the idea of A plus BI without trying very hard. It's just come out naturally from solving that quadratic equation. It always seems to me to be a bit strange that if you introduce I to be a square root of -1, that's fine. But why would you write 2 plus I to be a complex number, or A plus BI to be the general complex number? And here it is, it's just appeared quite naturally through what I already know about solving quadratic equations. Of course, you have to explain a bit that plus sign in A plus BI. It's not very clear what it means, that you're adding a real number and a multiple of I, but nevertheless, it is a natural thing to do. And so maybe that's an approach worth thinking about. Now, here's another section of the AS MEI Further Maths spec. We had some choices about what we put in AS Further Maths, and some limited choice, and properties of roots of quadratics and cubics as well, and quartics is in the spec. There's a little section of the spec, and I just want to pick out the line that I've written underneath. The roots of ax squared plus bx plus c equals 0 have that as their sum, negative b over a, and their product is c over a. So let's apply that. Supposing we've learned that. It's not too hard to show, is it? Just multiply out x minus alpha, x minus beta, and see what happens. But let's apply that, what we've learned there, to this quadratic, x squared plus 6x plus 13. And the sum of the roots is negative 6, and the product is 13. So I'm trying to think to myself, what does that tell me about the two roots? If their product is 13, well, that means they're either both positive or both negative, but the sum is negative, so they better be both negative. So are there two negative numbers which add together to give negative 6 and multiply together to give 13? And I might play around with that for a bit and wonder if I can find some numbers, and I can't. So I try the formula, and I use the ideas from the previous slide, and these are the answers I get: negative 3 plus 2i and negative 3 minus 2i. And so now I'm going to ask these questions here. These two numbers, is it true that they have a sum of negative 6 and that they have a product of 13? I've not taught anyone yet how to add and multiply complex numbers. This is the point. This is me introducing how to add and how to multiply complex numbers. Because I want it, whatever you do, however it works, adding and multiplying these strange numbers, I want it to work so that those two numbers add up to -6. Any good ideas how that might work? And I want it to work so that when you multiply them, they give an answer of 13. And it turns out, of course it turns out, that the ways we teach, the ways we know of adding and multiplying complex numbers work. You multiply out two brackets, for example, almost treating I as if it were, well, any number or even an algebraic quantity, and it works. But it appears to be, it makes sense that it works. It makes sense. I've got a reason now for believing that's a sensible way of adding complex numbers and of multiplying them. What's more, these two numbers, -3 plus 2i and -3 minus 2i, should satisfy my original quadratic equation. It should be true that when I square one of them and add 6 times it and add 13, I get 0. So is this true? And it's easy enough to show that the rules for adding and multiplying complex numbers do indeed make that work. So maybe that's not a natural order, and I was looking at a scheme of work the other day that put properties of roots of quadratics or of polynomials later than complex numbers. And I just wondered to myself whether there's some value in actually doing it the other way around, that it might give you some access to a way of motivating, justifying some of the rules we have for complex numbers. Okay, I'm now going to go on to an exam question from the specimen papers, from the AS Further Maths MEI specimen paper. And here it is. And I want to say just a little bit about it. So a cubic equation, and it looks like a roots of polynomials equation. Question, roots of polynomials equation. That's fine. Presumably at somewhere you're going to use the properties for some of the roots of a cubic. Maybe that would help you find alpha, knowing that the sum of these is 4. And perhaps we'll use something else to find P. We can get a sense for how this is going to work. Here's the mark scheme to save you having to work it all out. And it turns out that alpha and 2 over alpha are not real numbers. You need to delve into complex numbers, 1 plus I and 1 minus I, and the other root is 2. In fact, with this question, there are many routes through the question. And I think it's going to be a bit of a rule that when you see a question with bullet points like this, it's not trying to suggest the order in which you might tackle it. It might be that you could find P first before you find the roots of the equation. But there are several different ways through this question. And here is a mark scheme. These 3.1s and 3.2s over here, that means assessment objective 3. This is a problem-solving question. Some of the marks are assigned as problem-solving marks. Because at some stages, it wasn't particularly clear what you had to do. It wasn't straightforward. So what is it about this question that I particularly wanted to point out? Well, I suppose the first thing I wanted to say is that complex numbers is perhaps a bit of a surprise. All the questions I can think of from live exam papers that are about this topic, about roots of polynomials, we don't seem to bother too much about what the roots actually are. And we don't seem to get into complex numbers. And here we have. And actually, we've done that because, and this is public knowledge, one of the rules about all qualifications, not just in maths, but all qualifications, all A-level qualifications, is that candidates have to be able to draw together different bits of their learning, their knowledge and their skills and their understanding to answer some questions. And here we've done that. We have to do it somewhere, so here we are. We've done it here. They've brought together the knowledge of roots of polynomials and coefficients of roots of polynomials and complex numbers. So that's one of the reasons that the question was designed as it is. Actually, it's interesting trying to write the question. Can you see why the first version there wouldn't work? I couldn't possibly have a question that started like that had complex roots. And the reason is that we need conjugate pairs, of course, and you can't have alpha and alpha plus 1 as a conjugate pair. Whereas you can, in the second one, which is actually the question we've just been looking at, you can have alpha and 2 over alpha as a conjugate pair, and that's actually how it works. And of course, if you add two numbers which are a conjugate pair, you get a real number, and that's how it turns out that the other root, alpha plus 2 alpha over alpha, is a real number, which you need for a cubic with real coefficients. So actually, it was quite a challenge to write this question. We learned quite a bit in trying to do so. And I think a thing to learn when teaching your students is that there is this requirement that there are questions which bring together different bits of maths. That's a good thing, I'm sure. And complex numbers popping into a question when you didn't necessarily expect it might be something that happens, as it does in this question. I'm going to finish off with just one last little thing about complex numbers. It's just something I was thinking about the other day. And I think, again, as I reflect back on my own teaching, I don't think I ever quite made this clear enough. What about inequalities? So here on the left-hand side of this screen is a perfectly good solution of an inequality, a quadratic inequality. And in fact, I was helping the son of a friend doing a bit of GCSE maths, and this is what he was doing, and this is the sort of solution he wrote down. And that all seems fine, and the method he'd been taught to decide which way around the inequality goes is to try a number. So there he is. He's got the roots of the equality as being 3 and 1, so he'll try 2, and that works. If you put 2 in, that gives the quadratic as being less than 0. So he knows from that that the solution to the inequality is x is between 1 and 3. So that's fine. What about this inequality? It's almost the same inequality, isn't it? I've changed the +3 to a +5. So I'll just start the same method. This year 11 son of a friend might be doing this in a few months' time. But I get into trouble. So I get 2 roots, 2 plus I and 2 minus I. So I'll do my GCSE technique. I'll try 2, and it doesn't work. So I'll just do the obvious thing and say that it must be outside of that region. X is bigger than 2 plus I, X is less than 2 minus I. And of course, that's all nonsense. It is all completely wrong. Inequalities don't work with complex numbers. And I don't recall in my teaching making that clear enough. It's not true that 2 plus I is less than 3 plus I. It just doesn't have any meaning to talk about inequalities with complex numbers. You can talk about inequalities. The modulus of this complex number is less than the modulus of this one, and we do that with loci on the Argand diagram. You could talk about the argument of a complex number being less than the argument of a different one. Again, that could be a loci question, couldn't it? But the inequalities between complex numbers, I think sometimes I would have forgotten to talk to my class about that, and maybe it's worth pointing out so that they don't make silly mistakes like I appear to have done on the right-hand side of this screen. I'm going to stop pretty soon. I'm just going to leave that slide there, which is a link to the page, the web page I showed you earlier, and my email address. Please do email if you have any questions or want any help. And I'll just have a look at the chat box and see if there's some questions that I can easily answer. If I don't answer your question, please do email me, get in touch if you'd like to. I need to slip away a little bit early, so you may know I'm presenting in another webinar at 5 o'clock. I just need to set that up. So a few questions here. Is finding roots of complex numbers on the MEI spec, as in roots of unity, if that's what the question means? Yes, it's in the A-level further maths. I'm pretty sure it's part of the mandatory content, but we've not put it in AS. So we don't have any choice about the 50% pure in A-level further maths, but we did have some choice about AS further maths, what pure went into that. So you will see differences between the spec. So a comment there. Is it still okay to write solutions in inequality versions rather than using set language? That's interesting, isn't it? Because there's this specific thing in the ALCAB rules about using proper notation, set language notation for inequalities. And I think the thing to do, rather than me try to say it here, because it's quite hard to speak when I want to write something down to show you, is to say, if you find a mark scheme, we've deliberately put a question in the maths specs where the answer is an inequality. And in the mark scheme there, we have put different versions of different ways that will be accepted for writing the inequality. And obviously that's been accredited by Ofcom. And if you'd like to email, if you can't find that, then email me and I'll send you a link or cut and paste a clip that shows you that. It's quite hard to read it out on a webinar like this. So thank you for that. Someone's pointing out that you can't order complex numbers in the same way as you can't order vectors. That's neat, thank you. I'm just not sure that I used to say that kind of thing to my classes. I suppose with complex numbers, I'm calling them numbers. And it's a great temptation to say that 2 plus I is less than 3 plus I, but I mustn't. And I think I ought to say that to students. Please, so a request here to share the question about the GeoGebra questions that I was asking at the beginning. Sure, I'm very happy to do that. Either email me and I'll send you the slide, or this whole webinar is being recorded and will be available very soon from OCR. I think they will automatically send you, if you've been at this webinar, they will also automatically send you a link to the recording of it, and you could quickly go through that and find that question. Are these sessions recorded? Yes, yes, indeed they are. OCR will send you a link. Right, you mean finding x such that x squared equals 3 plus 2i. So that's not explicitly written down in the MEI spec, I mustn't comment about whether that question could be asked, because it wouldn't be appropriate for me to say what might or might not be in an exam. I think if I were a teacher and that question were asked, depending on the context, if it was the first question in an AS paper, I would write to the exam board and complain. If it felt like a problem-solving question later on in the paper, you know, in the context, depending on what part 1 and part 2 was, if this was part 3, that might seem quite an interesting problem-solving question. And here I've got some suggested answers to the locus, but thankfully they've come through privately, so the rest of you will have to work it all out. But that's interesting. I haven't worked it out myself yet, so thank you for that, the person who sent me that in. Now, I think I'm going to slip away now, if I may, and I think Will has something else to say, so I think I can pass over to him. Thank you ever so much for coming along. I hope it's been of some use to you, some interest. Have a good evening. Bye-bye.
Thank you very much, Keith. It's a fascinating presentation. Lots of really useful ideas there about the pedagogy around complex numbers and rich polynomials. So excellent stuff. Those of you who are wondering where Keith is off to now, he's about to go across to a separate room for his webinar at 5 o'clock. If you're joining him for that, you will need to leave this room and then enter the other room. So you can't just hang around here and hope that he reappears. As Keith said, we've got a couple of things just to pick up on at the end. There's a few questions here that I can answer. I've got one here that says, are these sessions recorded? Yes, they are recorded, and at some stage very soon those recordings will be available on the OCR website for you to go through again and to view any webinars that you've missed. So this is day 2 of the Festival of A-Level Maths. At the end of the week on Friday, we have a free day in London at the Emirates Stadium, where there'll be lots of presentations on specifications, on maths and further maths, but also on teaching using large data sets and on teaching mechanics using technology and so on. All our publishers, Casio and Texas and so on, will be there with their exhibitions. It looks like a great day. So if you are able to get out on Friday the 9th, it'd be lovely to see you there. And you can of course come and bother OCR and MEI staff with your questions. We also have some CPD trainings, face-to-face CPD events. These are more to do with specification A, but coming up in June and July, presented either by myself or by Stephen Walker, and full day free CPD sessions, hands-on, looking at mathematics in the morning and further maths in the afternoon, doing some practical activities, doing some large data set work together, and looking at schemes of work and scheduling of the curriculum. If you're planning to teach OCR or MEI maths, further maths, do please let us know. You can follow this link to ocr.org.uk/teachwithocr, and let us know. That then gets you signed up to our updates and so on, as another source of free resources and so on to go with the MEI staffing that Keith already mentioned. So do please go to the website, A-Level Maths, and download specifications and sample assessment materials. Sign up to CPD training, the CPD, and if you have any questions for OCR, you can always get in touch with us at maths@ocr.org.uk. There's 2 more days of webinars. Tomorrow looking at the large data set, at calculated use and technology, and on Thursday looking at mechanics and underground maths. On webinars. So I'll finish there, so there's plenty of time for those of you who are moving on to the next session. I'll stay here for another 5 minutes in case there are any further questions. Otherwise, thank you very much for coming, and shall see you on at a face-to-face event at some stage. Thank you.
Okay, thank you, Will. And just to note that once we close the session, a feedback form will pop up on your screen automatically. We do welcome any feedback and comments that you may have related to the webinar sessions that we have, as well as to the overall Festival of Maths and well, the A-level math specification and further math specification if you so choose to include that information. We do hope that you found the session to be useful. As Will mentioned, he'll be sticking around for the next few minutes if you do have any additional questions related to today's presentation or any other details related to the A-level math spec. Okay, as mentioned, once we officially close the session, the feedback form will pop up. Thank you.